Okay, time to talk voltage drop. Everything we've done so far has been about making sure our systems are safe. Sufficient conductor ampacity, protected by the overcurrent protection device, the terminals aren't going to be overheated, NEC requirements for safety. Voltage drop is all about making sure systems work well. The NEC is not really necessarily concerned about that. They're concerned about safety. We want to make sure we limit voltage drop because it reduces power loss. And also, if we have too much, we can have some major issues in terms of inverters not operating, shutting down, that sort of thing. So have to consider voltage drop, not a code requirement, but critical to good system design. Sometimes we'll find out that in order to have acceptable levels of voltage drop, we need a bigger wire. We need a bigger wire, in which case we'll increase wire size so that we hit that voltage drop target. Bigger wire, if it was already big enough for the circuit current and we did all our calcs right, then going bigger is not a problem. Can't go smaller. If I'm like, oh, this wire that is sufficient for ampacity gives me such low voltage drop that I could make it smaller. No, you can't. You can't, right? We have a minimum for the ampacity. And what we're saying now is that if that minimum size wire for the circuit current and the required ampacity gives you too much voltage drop, well, then you go bigger to make sure that you have a well-designed system. Can't go smaller, though. So what are our acceptable voltage drop values? These are not necessarily hard targets, but sometimes they might be, more so than others. Got to keep in mind, this is additive across a system. We usually break these down into two parts, the DC voltage drop and the AC voltage drop. They come together in the inverter, but we've got different things to think about in terms of them, and the calculations will be a little different as well. So they're additive across the system, right? From the modules to the combiner, to the recombiner, to the inverter. From the inverter output to the point of interconnection, wherever that may be, right? And that can vary considerably depending on what kind of system you're working on. We really want to minimize it to within acceptable limits. And these limits come from general guidelines. I'm about to give you some. They come from manufacturer requirements. We'll talk about those. And they also come from a cost-benefit analysis. There becomes a point where there's diminishing returns from increasing our wire size in terms of the voltage drop, the lower voltage drop we get. Of course, we can always reduce it, but at some point, we're buying more wire than we're gaining in output of the system. So in that case, the cost-benefit analysis says no, and we don't necessarily want to go there. General guidelines would be, hey, DC side of the system, 2 to 3% is kind of what we see targeted. Back in the olden days, I'm making air quotes, when PV modules were super expensive, maybe people would be taken aback by a 3% voltage drop. Larger systems these days, we see it being pushed even higher because it's that cost-benefit analysis of wires that are going to be sitting there all the time. Sometimes there might be a little more voltage drops, other times not. It depends on what the system's putting out. Is it worth it? Is it worth it? On a large system, doing that analysis really makes sense. Smaller systems, a lot of times, well, okay, we'll just throw a bigger size wire at it. It's not that much. It's going to be fine. It's going to make it work better. The AC side is a little more critical. We target about 1% from the inverter to the point of interconnection. And that's a great target. You really want to pay attention to what your manufacturers say. If you think about it, voltage drop from the inverter to the point of interconnection. If we have some percentage of voltage drop from the output of the inverter to here, well, I'm losing voltage. It's going down as I get to here. What does that mean on the inverter end? It means the voltage at the output terminals of the inverter is higher. It's essentially the grid voltage accounting for the voltage drop back to the inverter. So it's going to be 1 or 2% or whatever that AC voltage drop is above grid voltage because we lose it by the time we get to the grid. That's our drop. Well, a lot of inverter manufacturers are going to say, you got to minimize this to 1 or 1.5%, whatever it is. The issue being that, well, if the grid voltage itself is high and the inverter's got to be above that grid voltage to push current towards the grid, well, now all of a sudden with high grid voltage and voltage drop, I may end up having a voltage at the output terminals of the inverter that's above the rated voltage it can operate at, right? A 240 volt inverter, if it sees 264.1 volts at its output terminal, it shuts off. That's a high grid voltage shut off. So really important to keep this in mind. Really We've got a little more wiggle room on the DC side. It's power loss, but it's usually not extreme enough to do things like fall out of the inverter MPPT window. The AC side can be much more fickle, depending on the voltage at the site. You can get into a problem where when the inverter is really pushing out a lot of current, that we can run into an issue where we often call voltage rise, where the terminals of the inverter see that higher voltage and it shuts off as a result. What about the values we use when we're looking at voltage drop? It's going to depend on the circuit voltage and the circuit current. So we want to make sure we base our calculations on the right values for the circuit we're working on. For DC PV circuits, we're going to use the array maximum power voltage and the array maximum power current. That's what we expect the array to be able to make. Is it always going to make those numbers? No, sometimes it's going to be less. Sometimes it might be a little more. We might have a little more voltage drop than we calculated, but these are good conservative targets. If you want to go more conservative, if you're in a really high temperature location, for instance, then temperature adjusted VMP would be a way to account for that, or using short circuit current, which is going to be higher than maximum power current. That'll also be a way to kind of build an extra level of being conservative into the design. If I have less voltage and more current, then the calculation is going to show more voltage drop, and then I'm going to pick a wire accordingly. So again, recommendations for most cases, just to use array VMP and array IMP. On the AC side of the system, for our inverter output circuits, we're going to use the nominal AC system voltage as our circuit voltage, and we'll go back to using the inverter continuous output current as our circuit current. Same number we started off with talking about calculating maximum circuit current. We base it all on the inverter continuous output current. Same thing here when we do our voltage drop calculations. There's a lot of different ways to do voltage drop calculations. A lot of different ones. Get on the interwebs and take a look, and you'll see all kinds of different formulas. Some that become really advanced engineering applications, other ones that are just different ways of stating the same formula mathematically. The one we use at SEI on the screen here, we are going to say that for DC and split phase, so non-three-phase AC, our voltage drop as a percentage calculation is going to equal 0.2, that's a constant, times the distance, times the current, times the resistance, divided by the circuit voltage. So there's our table. Distance, one-way distance in feet. So we're working in feet here. One way, not round trip. Operating amps. We just talked about what do we use? IMP for PV circuits, rated continuous output current for our AC side of our systems. The R is resistance, and this is specifically the resistance of the wire in ohms per 1,000 feet. Ohms per 1,000 feet. Ohms per kilofoot. Don't see that one too often. This is given to us in the National Electrical Code, Chapter 9, Table 8 for DC, and Table 9 for AC. So we just need to look up this value based on the conductor that we're using and whether it's in a DC or AC circuit. And then our last variable is the voltage of the circuit itself. Again, we talked about that. VMP for PV circuits, nominal AC system voltage for AC circuits. If we're looking at three-phase, the constant changes 0.1732 instead of 0.2. Some of you are probably looking at this and being like, that's not the voltage drop calc I know. Yeah, it's math. There's so many ways to rearrange formulas and do things differently. We've tried to take a lot of the labels out of this so that you can just find numbers and drop them into the equation. There's lots of voltage drop calculators out there and spreadsheets you can make and other ways to figure out this number. Voltage drop is a percentage. These work, easy to use. All you need to do is track down the data and drop it in. Let's do that with an example for a PV source circuit. We're going to calculate voltage drop as a percentage. So we've got our 10 AWG conductor. We figured out that that was going to be good for this PV source circuit. We've got a 200-foot one-way wire run. So remember, we're just looking at our one-way distance. Circuit IMP, 8.81 amps. Remember, not short circuit current. That's what we've used for everything so far for sizing wires and breakers and fuses. But now we're looking at operating conditions. So maximum power current for that same module, 8.81 amps. And however many of them we have in series, we've got a circuit VMP of 518 volts. So these are STC values, right? These are not temperature corrected or adjusted for irradiance or anything. These are off the spec sheet for current. And then for voltage, it's, well, the voltage of 1 times however many are in series. Last piece of information I need, the resistance of my 10 AWG copper conductor. We go to Chapter 9, Table 8, and we look down here for uncoated conductors. That doesn't mean uninsulated. It means it doesn't have a conformal coating over it that you might see in conductors and transformer wirings, for instance. So that's what we'll be using, uncoated conductors. Make sure you're in the right column, copper or aluminum. And we see that we have a resistance of 1.2 ohms per 1,000 feet. Now that we have all our data, we can drop it into our easy-to-use formula here. So we've got our 0.2 constant. We have our 200 feet of one-way distance, 8.81 amps. Remember, that's maximum power current, times the resistance of the wire, 1.24 ohms per kilofoot. And then we divide that by the VMP of this PV circuit, 518 volts. Come up with a voltage drop of 0.84%. That sounds good to me. Less than 1, great. We're doing good here. 10 AWG wire is big enough for it. The ampacity has enough ampacity as we calculated already. And we've made sure that the voltage drop that we get with that size wire is adequate for the circuit. Could we go bigger and get less? Yeah, probably not going to be worth it from a cost standpoint. Could we go smaller? No, you can't. 10 is the smallest you can go for the ampacity. Even though a 12 AWG conductor would probably still end up giving you an okay voltage drop, it doesn't have enough ampacity. Can't use it. If we decided we wanted something bigger, we could go there. We can't go smaller. In this case, 10 AWG works for both the ampacity requirements and the voltage drop requirements. Okay, that was voltage drop as a percent. We can do that for DC circuits, split phase AC, three-phase AC, but we could also do the calculation, flip it around a little bit, to solve for the resistance of the wire that we need. So what's the required conductor resistance to not exceed a maximum voltage drop level? This is something you might see on the AC side of systems in particular. Manufacturer says no more than 1% or no more than 1.5% AC voltage drop. That's what we're shooting for. So what size wire do I need to get that? Right? Instead of saying, well, this wire gives me this much and this wire gives me this much and this gives... No, it's just say, find a resistance value and then look up a conductor that meets that level of resistance. So the values here are the same. We're going to say, what's our required voltage drop? What's our circuit voltage? Again, VMP on the DC side, nominal AC voltage on the AC side. We have a constant of 5. Again, that was just derived algebraically by getting rid of some of the labels that are attached to these values. We've got our operating current, again, IMP for PV circuits, rated continuous output current for inverters, and our one-way distance, again, in feet, one-way only. This calculation, if you are working on three-phase circuits, change that constant to 5.774. Let's look at an example. Now we're looking at an inverter output circuit, and we want to say, hey, what size conductor do I need to not go over a certain amount of voltage drop? In this case, we're targeting 1%. We've got an 80-foot long run. That's our one-way distance. The rated continuous output current of the inverter is 32 amps, and we are operating at 240 volts AC. Here's our calculation. We're going to solve for ohms per kilofoot, and then we'll go to our table to see what conductor meets that. We drop in our values, 1% target voltage drop, 240 volt nominal AC circuit, 5 is our constant. We divide that by the rated continuous output current of the inverter in this case, 32 amps, and the one-way distance of 80 feet. Do the math, and we say that, hey, we want a wire that has a resistance of no more than 0.469 ohms per 1,000 feet. Go to the table, and we see that kind of fell in between. So we're in Chapter 9, Table 8 here. We see Table 9, I'm sorry, because we're doing the AC side. So our 6 AWG conductor is a resistance of 0.49 ohms per 1,000 foot, just a tiny bit above that 0.469 that we got when we solved our equation. And if we go to the next bigger size, we're looking at a 4 AWG conductor, which has a good bit less, 0.31. So 0.49 with the 6 AWG conductor and a little more resistance is going to mean we're going to have a tiny bit more than 1% voltage drop. 4 AWG conductor, less resistance than we solved for, we're going to have a less than 1%. We need to decide which one is sufficient. This is kind of an edge case here, right? The 6 is going to give us just a tiny bit over 1%. The 4 is going to give us way less. which one do we go with? Well, here, think about some things. Is that 80 feet one-way distance real, or is that kind of ballpark? How often is the inverter going to actually be operating at 32 amps? Could depend on the array size connected to it, the location of the system, angle and orientation, those kind of things. You can also take these resistance values that we just looked up for 6 and 4, drop them back into the previous equation, and see how much you really get. Like, what am I going to get if I use 0.31 ohms per 1,000 foot? What is my percent voltage drop? It's going to be less than 1. If I use 0.49 with the 6 AWG conductor, it's going to be more than 1%, but probably just a tiny, tiny bit. We have a decision to make here. What's it going to be? Again, there's not a right answer. A lot of it's going to depend on system specifics and how accurate your measurement of that length was, those sort of things. As long as either one of these wires is suitable for the circuit current, then we'll be fine. If a 6 can handle the current, maybe we put in a 6 and call it okay on the voltage drop. If 6 can handle the current, but we're like, oh, you know what? That distance, now that I look at it, is more like 92 feet actually, then we're probably going to go with the 4. So decisions you got to make as a system designer. Okay, up next, we'll do a little summary of the steps we've gone through, and we'll talk about some other considerations for sizing conductors and OCPDs. Catch you there in a minute.